we built the most powerful time machine in history. A $10 billion engineering marvel, waiting in the absolute darkness 1.5 million kilometers from Earth. But this flawless machine brought us a signal that physics forbids: a light. Yes, the photons reaching Earth right now should not exist. Because this light has been traveling for 13.5 billion years, coming from a moment when the universe was only 300 to 400 million years old. At that moment, a galaxy so bright, so massive, filled with billions of stars, could not have formed. This is more than a discovery. But what's truly unsettling is the confirmation that this was not a mistake. This leads us to the most fundamental question. What if the beginning wasn't what we thought it was? If you're excited to chase this impossible light, wow, like and subscribe. Because your beliefs about the Big Bang are about to be fundamentally shaken. Let's begin. For years, we searched for an Earth twin. It had to be a rocky planet, orbiting a sun-like star. And it had to be at the perfect distance for liquid water. This seemed like the only way to find life. But the James Webb Space Telescope peered into the depths of the Leo constellation. It found something there, 120 light-years away. And everything we thought we knew changed suddenly. Because the most habitable world in the universe looked nothing like Earth. Behold the first astonishing fact. K218 Sep-B. This is not an Earth twin. It's an entirely new class of planet. Scientists call them super-Earths. These worlds are larger than our planet, but smaller than gas giants like Neptune. K2-18b is exactly 8.6 times more massive than Earth. This is a huge difference. The gravity on its surface is nearly 3 times ours. So, a person weighing 68 kilograms on Earth would feel heavier than 180 kilograms on K2-18b. This is a crushing weight. But, until recently, astronomers considered such planets uninhabitable. They thought they were too big. They believed they were too gassy for life. So, they pushed them aside. K2-18b completely shattered this assumption. Because this massive size might not be a curse for life, but a blessing. This crushing gravity holds the planet's atmosphere like an iron fist. It prevents the kind of leakage that caused Mars's atmosphere to escape into space billions of years ago. Therefore, K2-18b can protect its atmosphere for trillions of years. This means an almost infinite amount of time for life to evolve. But the real question was, how could such a large and strange planet be habitable? The answer lies hidden in the planet's second surprising feature: its temperature. When James Webb analyzed the atmosphere of K2-18, it made a measurement with incredible precision. The planet's surface temperature was a constant 49 degrees Celsius. This number is not a coincidence. It's a magical setting for life. Not too cold, so water doesn't freeze. But not too hot, so water doesn't completely evaporate. What provides this perfect balance is the planet's atmosphere. Unlike Earth's thin nitrogen atmosphere, K2-18b is covered by a thick blanket of hydrogen. This atmosphere creates a greenhouse effect. But not a runaway hellscape like Venus. Instead, it acts as a perfect insulator. It distributes heat so efficiently across the entire planet that even its dark side, which never sees its star, remains warm enough for liquid water. K2-18 orbits a red dwarf star called K2-18. This star is smaller and cooler than the Sun. But the planet is so close to its star that it completes one orbit in just 33 days. Thanks to this proximity, it receives almost the same amount of energy as Earth does from the Sun. Therefore, despite being 120 light-years away, it exists in the same thermal environment as we do. This is not a cosmic coincidence. This was a result of physics. So, what did this perfect balance and strange atmosphere mean? The meaning lay in the third and most mind-boggling fact the telescope found. Dimethyl sulfide. This might sound like a chemical tongue twister, but these two words could be the most important discovery in human history. Because when James Webb detected this molecule in the atmosphere of K2-18, it found something that no known non-biological process could produce. It found the signature of life itself. On Earth, dimethyl sulfide is produced only by living organisms. The phytoplankton in our oceans release this gas into the atmosphere as a byproduct of their metabolism. Marine bacteria, certain types of algae, and even plants produce this molecule. But no geological process, no chemical reaction, no non-living system creates this molecule. Therefore, finding it in the atmosphere of another world was like finding a giant, flashing neon sign with a single word written on it: life. And this wasn't just a trace, Tikaus. The signal was so intense that scientists are 99.7% sure. This is a level of confidence almost unprecedented in astronomy. The probability of it being an error is less than 3 in 1,000. This is a statistical threshold known as a 3 sigma detection. So, the chance of this discovery being a coincidence is even lower than the chance of flipping a coin 1,000 times and getting heads 997 times. So, what do we have? A massive planet, nothing like Earth, a stable, warm temperature across its entire surface, and a chemical that can only be produced by life. These 3 findings have fundamentally shaken our view of the universe. We are no longer searching for an Earth twin, because life had blossomed in conditions we never expected or even imagined. But how could this enormous mass, crushing gravity, and suffocating hydrogen atmosphere create a paradise instead of a hell? The answer lies in the planet's most bizarre feature: its ocean of water and hydrogen. An ocean that is unlike anything we know, and this ocean could make K2-18 be the most habitable world in the universe. Because this isn't just an ocean of water. It's a brand new type of liquid where water and hydrogen merge under incredible pressure. This exotic hydrogen ocean creates one of the most favorable environments imaginable for life. On Earth, the deepest points of our oceans have about 1,000 times atmospheric pressure. This is a force that would instantly crush the cell structures of most life forms. But on K2-18b, the situation is different. The dissolved hydrogen in the water acts as a natural pressure buffer. This allows the ocean to maintain conditions similar to Earth's surface pressure even at much greater depths. This mixture allows water to remain liquid over a much wider temperature range than its pure form. This hydrogenated water can stay liquid from its freezing point up to 149 degrees Celsius. This offers a huge range of conditions where life can thrive. But this ocean's greatest trick is protecting the planet's atmosphere. Earth's atmosphere is slowly leaking into space. In billions of years, our planet will become as dry as Mars. But K218b's hydrogen ocean acts as a giant atmospheric reservoir. As hydrogen escapes into space, more evaporates from the ocean to replace it. Therefore, the planet can maintain its atmosphere for trillions of years. This means an almost infinite amount of time for life. But to live for that long, it needed a stable energy source. That source was the star K2-18b orbits. K2-18, this is not a star like our Sun. It's a red dwarf, the most common type of star, what seems, making up about 75% of all stars in our galaxy. Red dwarfs are smaller, cooler, and much dimmer than the Sun. But their most important feature is their incredible longevity. While our Sun has a lifespan of about 10 billion years, a red dwarf like K2-18 can shine for 10 trillion years. That's a longer period than the current age of the universe. This mind-boggling longevity has profound implications for life. On Earth, it took complex life almost 4 billion years to evolve from simple bacteria to today's ecosystems. If life on K2-18b has had even a fraction of that time, it could have reached a complexity beyond our imagination. Many red dwarfs are known for violent flares. These flares emit radiation powerful enough to sterilize nearby planets. But K2-18 is a type of red dwarf that astronomers call well-behaved. It shows minimal flare activity. This allows its planets to keep their atmospheres and potentially sustain life. This stability is a critical factor, not just for life to emerge, but for it to thrive. This means the most common type of star in the universe might also be the most promising place for life. So, what about the proof? These perfect conditions would remain just a theory without concrete evidence. But one of the strongest pieces of evidence was not something Webb found, but something it did not find. This was the mysterious absence of ammonia. If K2-18b were a lifeless gas giant like Jupiter or Saturn, you would expect its atmosphere to be filled with ammonia. Because this molecule forms naturally in hydrogen-rich atmospheres. But James Webb's spectral analysis showed a glaring lack of ammonia. It was missing from where it should have been in the atmosphere. This was not a mistake. This was the most important piece of the puzzle. Because this indicates that something on the planet is actively removing ammonia from the atmosphere. And the most likely candidate known? Life itself, even on Earth. Biological processes constantly alter atmospheric chemistry. The absence of ammonia on K2-18b suggests that the planet not only hosts life, but that life is actively shaping the planet's chemistry. This is evidence of a planet-scale metabolism. Life doesn't just exist there. Life is managing the chemistry of an entire world. This is something beyond a biosignature. It's a bioactivity signature. This was the strongest evidence to date that we are not alone in the universe. So, all the pieces are falling into place. A habitable super-Earth, many times larger than our own. A hydrogen ocean that could protect the planet for trillions of years. A stable red dwarf star providing almost infinite energy. And a chemical cocktail that can only be explained by life. The presence of dimethyl sulfide and the absence of ammonia point to a single conclusion. But all these incredible inferences are based on a faint flood of photons from 120 light-years away. Yes, so. What did James Webb actually see to draw these revolutionary conclusions? How did the telescope gather this data? Because it's one thing to say a planet might have life, but the technology and analysis required to prove it with 99.7% certainty is something else entirely. And the details of that proof were far more shocking than the theory itself. Because it's one thing to imagine something is possible, but it's another thing entirely for the universe to scream at you with evidence that you were wrong. James Webb looked, and the scientific world was shaken. Theories fell short. Here are Webb's findings. This is a photograph of the impossible. It all started with that number, 99.7%. That was the confidence level scientists had that the dimethyl sulfide signal in K218b's atmosphere was real. This was no ordinary confidence level. This was a 3 sigma detection, the statistical threshold required for a discovery in physics and astronomy to be considered the gold standard. To understand what this means, imagine flipping a coin 1,000 times. The probability of getting heads 997 times is so low, it would not happen by chance in the entire history of the universe. That's how certain this signal was. This shouldn't have happened. Because, in astronomy, especially in the search for life, there's almost no such thing as certainty. Findings are debated for years. Signals turn out to be just noise. But not this time. This signal wasn't a whisper. It was a scream, and this scream was only the first shockwave. Those numbers on Niku Matsuda's screen at Cambridge University were mathematically declaring the end of humanity's cosmic solitude. Therefore, scientists analyzed the data again and again. But the result did not change. The probability calculations left a margin of error of only 3 in 10,000. This was evidence as certain as the existence of DNA, as solid as the theory of relativity. But how? How could such definitive proof be found on the very first look? The answer lay in the planet itself. Because Webb didn't just see the chemicals, it saw the planet itself. And what it saw challenged the known laws of physics. K2-18 had a hydrogen ocean. This is not a water ocean. This was an exotic mixture of water and hydrogen. Unlike anything on Earth, this ocean could be hundreds of kilometers deep. That's thousands of times more water than all of Earth's oceans combined. This massive body of water explained the intense humidity in the planet's atmosphere. But the real impossibility was the behavior of this ocean. Under high pressure, the dissolved hydrogen completely changed the properties of water. This mixture could remain liquid up to 149 degrees Celsius. This offered an incredibly wide temperature range for life. But that wasn't its most mind-boggling feature. This hydrogen ocean acted as a giant reservoir, capable of protecting the planet's atmosphere for trillions of years. This should not have been possible. Because planets lose their atmospheres to space over time. But K218b had a system that constantly replenished its own atmosphere. This made the planet almost immortal. Therefore, life could have had the chance to evolve for lengths of time we can't even imagine. But Webb's shocks weren't limited to K218b. The telescope turned to another direction, to a young star system named CERN. It was only 6 million years old. A baby. And there, Webb found something it shouldn't have seen. More accurately, it noticed a gap that shouldn't have been there. The debris disk around the star was composed of 3 separate rings. But between the rings was a massive gap, a region millions of kilometers wide, Irene's almost completely cleared out. This gap theoretically should not have been there. Because gravity should have filled the entire disk with dust and rock. Something, like a cosmic vacuum cleaner, had cleaned everything in that orbit. And Webb detected the heat from the heart of that gap. It was a world that broke the record for the lightest planet ever directly imaged. It had only 1/3 the mass of Jupiter. This was an impossibility. Because seeing a planet that light next to its star's glare, which is 10 billion times brighter, was like looking at a single candle next to a stadium floodlight from across the country. But Webb saw it. This wasn't just finding a new planet. This was a brand new way of finding planets. We could now search not just for light, but for the absence of light. So, on one hand, a world that is 99.7% certain to be alive. On the other, the trace left by an impossibly light and invisible planet. All of them are findings that require us to rewrite the most fundamental rules of the universe. But all of this was just data from a single telescope. How was this possible? How could this machine analyze light so precisely? All these discoveries were actually just symptoms of a larger truth. The truth is, the James Webb Space Telescope is not just an observation tool. It is a machine that changes the very fabric of the universe, and its real secrets are hidden, not in the data it collected, but in how it collected that data. Its secrets lie in the structure of its mirrors, the coldness of its instruments, and its ability to bend light. And its real secrets are hidden, not in the data it collected, but in how it collected that data. And the first of these secrets was the shocking abundance of another chemical discovered in K218b's atmosphere: methane. Theoretically, methane shouldn't have been so abundant there. This simple molecule breaks down quickly under ultraviolet radiation. Therefore, to maintain its presence in K2-18b's atmosphere, it had to be continuously produced in enormous quantities. But how enormous? Webb's measurements showed that the planet's biosphere was producing many times more methane than all biological processes on Earth combined. This wasn't just a byproduct of life. This was a planet-scale industry. On Earth, methane comes from many biological sources, from bacteria in swamps to the digestive systems of cows. But on K2-18b, methane had become a fundamental component of the atmosphere. This should not have been possible. Because such a high concentration of methane pointed to a chemical imbalance. It should have reacted with other molecules in the atmosphere and disappeared. But it wasn't disappearing. This meant that life on the planet might not only be producing methane, but also using it as an energy source. Organisms could be breathing and metabolizing methane. This implied a completely alien biochemistry, unprecedented on Earth. But the real shock was something else Webb found in K2-18b's atmosphere: rain. But this wasn't the kind of water rain we know. This was diamond rain. In certain layers of the atmosphere, the pressure and temperature created the perfect conditions to compress and crystallize carbon atoms. These microscopic diamonds formed in the upper atmosphere and rained down toward the surface. On K2-18b, B odds diamonds could be as common as raindrops on Earth. This seemed impossible because this process required an incredible abundance of carbon and extremely specific atmospheric conditions. Webb's data showed that the planet's carbon cycle was completely different from ours. Carbon dioxide, hydrogen, and methane in the atmosphere were in a constant chemical dance. This dance acted as a factory, producing not only diamonds, but also the complex organic molecules necessary for life. This meant the planet's atmosphere was not just hosting life, but was self-producing the very building blocks of life. Therefore, the planet as a whole was behaving like a giant living organism. This finding overturned all our ideas about how a planet could become habitable, and Webb was just getting started. The telescope turned its eye to other corners of the galaxy, and everywhere it looked, it found an anomaly. In a dozen different star systems, a consistent, shocking pattern began to emerge. Within a sphere just 200 light-years in diameter from Earth, astronomers detected more than 50 potentially habitable planets. But the real discovery wasn't the numbers. It was the diversity of these planets. Super-Earths like K2-18b. Rocky planets, worlds covered in global ice with subsurface oceans. This should not have been possible. Because, according to standard models, habitable planets were supposed to be rare. But Webb's data said the exact opposite. Even our small corner of the galaxy was teeming with the potential for life. Each one a different evolutionary experiment. Planets around red dwarfs had stability for trillions of years. Those around larger stars offered perfect conditions for rapid evolution. This meant that life might not be an exception in the universe, but a rule. If our local neighborhood is this rich, the entire Milky Way galaxy, with its 400 billion stars, could be home to billions of living worlds. So, a world that is 99.7% certain to be alive. Diamond rains, gaps left by invisible planets, and a galaxy teeming with life. All these findings raise a single question. How? How does the James Webb Space Telescope, floating 1.6 million kilometers away in a darkness colder than Pluto, collect this impossible data? What is the secret of this machine? Because this is not just a telescope, it is a time machine, a chemistry lab, and a key that unlocks the secrets of the universe. And to understand how that key works, we need to go to its heart, to its gold-coated mirrors and ice-cold instruments. Because the real magic begins there, in the ability of those mirrors to transform light from billions of years ago into a whisper. But how does this machine work? What is the secret behind these seemingly impossible discoveries? Now, we slow down our pace a bit, and we look under the hood of the James Webb Space Telescope. Because these discoveries were not just a matter of luck. They were the result of decades of work and revolutionary technologies that pushed the limits of human engineering. And it all begins with the language the telescope uses to speak with the universe. Infrared light. James Webb doesn't see the universe the way we see it with our eyes. It sees with infrared light. This is a light invisible to the human eye. But it holds the deepest secrets of the universe. Just like a thermal camera, Webb detects the heat emitted by objects. This is a vital feature for analyzing the atmospheres of distant planets. Because when a planet passes in front of its star, a very small fraction of the starlight filters through the planet's atmosphere to reach us. Each molecule in the atmosphere absorbs specific infrared wavelengths like a sponge. Therefore, dark lines appear in the light reaching Webb, the fingerprints of those molecules. It's by reading these fingerprints that we understand what's in a planet's atmosphere. Webb's primary mirror is a full 6.5 meters in diameter. That's a mirror nearly 3 times wider than Hubble's. But its real marvel isn't its size. The mirror is made of 18 hexagonal segments, each coated with a microscopic layer of gold. Gold was chosen because it reflects infrared light with over 99% efficiency. When these 18 segments work together, they achieve such perfect alignment that they could detect the heat emitted by a bee on the surface of the moon. This is unbelievable precision. While Hubble worked with visible light, the expansion of the universe causes light from the most distant galaxies to shift to red and enter the infrared spectrum. Therefore, Hubble couldn't see the oldest galaxies. But Webb was designed precisely to see this infrared light. That's why it's more of a time machine than a telescope. But just collecting the light isn't enough. That light needs to be separated from the star's glare, which is billions of times brighter. This is where Webb's second technological marvel comes in. The coronagraph. See, this is an artificial eclipse system inside the telescope. Directly imaging a planet is like trying to photograph a firefly next to a stadium floodlight. The star's light is so overwhelming that the planet becomes completely invisible. The coronagraph was designed to solve this problem. In fact, this technology has been used for decades to study the sun's own corona, or crown. But Webb's engineers adapted this technology to hunt for exoplanets. At the heart of the system is a series of precise masks and mirrors that block light. When starlight enters the telescope, these masks are placed exactly over the star's image, blocking its light. But this isn't just a simple disk. It's a highly complex optical system that even accounts for the diffraction patterns of the incoming light. The slightest misalignment in the system, a deviation of just a few nanometers, could ruin the entire observation. Webb's coronagraph can achieve a contrast ratio of about 1 in 10 billion. That's hundreds of times better than Hubble's capabilities. That's why we could directly image planets lighter than Jupiter, which were previously known to exist only in theory. This technology didn't just allow us to find planets. It allowed us to see the debris disks around them and the gaps in those disks. This opened a brand new window into how planets are born. However, collecting the light and blocking the star are only 2 parts of the equation. To make such sensitive measurements, the telescope itself must be at a temperature close to absolute zero, as otherwise the telescope's own heat would drown out the faint infrared signals it's trying to observe. This is where Webb's most iconic feature comes into play, the massive sun shield. This shield is the size of a tennis court, and it consists of 5 layers. Each layer is made of a special material called capton, which is thinner than a human hair. Each of these layers reflects some of the sun's heat back into space. This 5-layer system is so effective that it creates a temperature difference of over 300 degrees Celsius between the side of the shield facing the sun and the side in shadow. The hot side of the shield can get above the boiling point of water, while the cold side drops to minus 233 degrees Celsius. That's even colder than the surface of Pluto. This extreme cold allows the telescope's instruments to minimize their own infrared interference. Therefore, it can clearly detect even the faintest heat signals from the most distant corners of the universe. Without this shield, all the data Webb collected would be lost in a sea of noise created by its own heat. It's like trying to silence the entire world to listen for a whisper. And Webb does this alone, 1.6 million kilometers away. So, a giant gold mirror that collects infrared light, a coronagraph that blocks the blinding light of stars, and a giant sun shield that keeps the telescope at a freezing cold temperature. When all these systems come together, Webb can see the universe with a clarity never seen before. But that's only half the story. Because collecting raw data is one thing. Uncovering the secrets within that data is something else entirely. And this is made possible by Webb's perhaps least known, but most revolutionary technology. It's artificial intelligence-powered data analysis algorithms. Because sometimes the biggest discoveries are hidden, not in what the telescope sees, but in a piece of software that finds what we cannot see. And how this software distinguishes false signals from real discoveries is an engineering marvel as brilliant as the telescope itself. This process isn't like finding a needle in a haystack. It's like finding the right needle among millions of fake needles. And this process forms the basis of Webb's reliability. Because that 99.7% certainty comes not from the raw data, but from the intelligent systems that sift through that data. And these systems constitute the telescope's fourth great technological secret. AI-powered data processing. Webb sends terabytes of data every day. This is an ocean of information too vast for the human eye or brain to analyze. This is where specially trained artificial intelligence algorithms come in. The first task of these algorithms is to filter out false signals, just like trying to hear only your friend's voice in a crowded room. This software detects false specks called speckle, caused by flaws in the telescope's own optics. Cosmic ray hits, or interference from Earth. These speckles can mimic a real planet signal. But by comparing data from millions of observations, the AI has learned to distinguish the subtle differences between what is real and what is fake. To analyze K, 218-bis-dimethyl sulfide signal, multiple, independent observations were made over months. Webb's different instruments repeatedly detected the same chemical fingerprint at different wavelengths. The AI combined these independent observations, mathematically eliminating the possibility that the signal was a systematic error or contamination. That 99.7% certainty is the result of this exhausting and meticulous filtering process. Therefore, this is not just an observation, it is a repeatedly verified finding. But Webb's greatest secret is perhaps its location. The telescope orbits at a special point, 1.6 million kilometers from Earth, known as L2. This is no accident. It's a point of gravitational equilibrium. At this point, the gravitational pull of the Sun and Earth exactly balances the centrifugal force needed for the telescope to stay in orbit. This means Webb can maintain its position with very little fuel. But that's not the main advantage. At the L2 point, the Earth, Sun, and Moon always remain behind the telescope, in the same direction. This allows the massive sun shield to block all three heat sources at the same time. Therefore, the telescope has a constantly cold and dark environment to observe the rest of the universe. If the telescope were in an orbit closer to Earth, the infrared light emitted by our planet would completely disrupt its observations, Just as light pollution in a city prevents us from seeing the stars, the L2 point is one of the quietest and darkest corners of the universe. And this is Webb's home. This gravitational haven also allows the telescope to have incredible stability. The telescope must maintain its position with millisecond precision. This is a level of accuracy equivalent to steadily aiming a laser pointer at a coin on the moon. The slightest vibration, the slightest deviation, would blur those delicate spectral lines and make the entire discovery impossible. Therefore, Webb's location is the cornerstone of its precision and reliability. When these technologies, namely infrared vision, the coronagraph, the sunshield, artificial intelligence, and the L2 location, come together, what emerges is much more than a telescope. It is a spectrometer that can read the chemistry of the universe. When Webb analyzes the light passing through a planet's atmosphere, it separates that light into thousands of different wavelengths, much like a prism separates light into colors. This process is known as transit spectroscopy. This technique is not new. But Webb does it with a precision previously unimaginable. Detecting the presence of chemicals in a planet's atmosphere requires measuring a light absorption of 1 part per million. This is like trying to hear a single person's voice in a stadium of millions of people. But Webb does it. The detection of molecules like dimethyl sulfide, methane, and carbon dioxide in K218b's atmosphere was made possible by this incredible precision. The spectrographs analyze the unique dark lines left by each molecule, their absorption spectrum. This spectrum is like a molecule's ID card. Webb can read these ID cards from 120 light-years away. This technology allows us to answer not only the question, what is there, but also, how much is there? This is vital for understanding the chemical imbalances in a planet's atmosphere. And the chemical imbalance on K218b was one of the strongest pieces of evidence for life. So, all these brilliant technologies work in perfect harmony to answer one of humanity's greatest questions. The golden mirrors collect the whispers of the universe. The coronagraph silences the screams of the stars. The sunshield provides cosmic silence. And the artificial intelligence finds the meaning within those whispers. This is not just a machine. It is a monument to human curiosity, perseverance, and intelligence. But all these technical details, all these engineering marvels, are preparing us for the truly exciting part, the discoveries themselves. Because, no matter how impressive the technology is, what truly matters is what it tells us. And the story Webb is telling is big enough to shake everything we know. Because now we have the tools, we have the evidence, and in the atmosphere of K218 be considered the most habitable world in the universe. We have concrete findings about how life not only exists, but is changing the entire planet. And the details of these findings are beyond science fiction. Because now it's time to dive even deeper into that chemical cocktail. Into the truths behind those diamond rains, those methane cycles, and those mysterious chemical imbalances. And now, it's time to dive even deeper into that chemical cocktail. Because, no matter how brilliant the technology, the real miracle is what it shows us. We are now cranking the tempo to its highest. We are now reaching the climax. Because the things Webb found in K218b's atmosphere were not just evidence of life. They were the manifesto of a completely new biology, an ecosystem that pushes the limits of our imagination. And it all started with that one molecule, dimethyl sulfide. But that was just the beginning. This was a revolution. Literally. Because when Webb detected the dimethyl sulfide signal, it didn't just find a molecule. So for the first time in human history, it found direct chemical evidence of biological activity outside of Earth. This was one of the most important discoveries in history. The signal came from 120 light-years away. This means it took the light 120 years to reach us. So, what we were seeing was the planet as it was 120 years ago. Even then, the signal was incredibly strong. The concentration of dimethyl sulfide in the atmosphere was many times greater than in Earth's atmosphere. This could only mean one thing. The biosphere on K218b wasn't just surviving. It was conducting chemical production on a planetary scale. This should not have been possible. Because dimethyl sulfide is an unstable molecule that quickly breaks down in the atmosphere. To maintain such a high concentration, the organisms on the planet's surface or in its oceans had to be working thousands of times more efficiently than the phytoplankton on Earth. How could this be possible? This suggested the entire planet was acting like a single, giant, hutch-breathing organism. When this finding was published in the journal Nature Astronomy, it created an earthquake in the scientific community. Astronomers, chemists, and biologists came together to understand what this data meant. But all analyses led to the same conclusion. This was the undeniable fingerprint of life. This was the moment our cosmic solitude ended. But the shock was just beginning. Because Webb saw not only what was there, but also what was not there. And this revealed a much bigger mystery. The absence of ammonia. This was negative evidence. But it was far more powerful than the positive evidence. According to theoretical models, a hydrogen-rich atmosphere like K218b's should have been full of ammonia. Because it's a natural result of the most basic chemical reactions. But in Webb's spectrum, there was no ammonia. Zero. This was against the laws of physics. It meant that something was actively clearing ammonia from the atmosphere. Millions of tons of ammonia were somehow disappearing. It was a cosmic mystery, and there was only one plausible suspect: life. This showed that the organisms on K218b were not only producing molecules like dimethyl sulfide, but were also actively shaping their environment. They could be using ammonia as a food source or an energy source. This was evidence of a self-regulating biosphere that was balancing the planet's chemistry. This was a planet-life interaction unprecedented even on Earth. This discovery caused a paradigm shift in the field of astrobiology. We were no longer just looking for traces of life. We were now looking for evidence of how life manages a planet. This solidified the idea that a planet could be not just habitable, but alive. And then, that number came. 49 degrees Celsius. Webb measured the planet's surface temperature with incredible precision, and the result was a perfectly stable 49 degrees. This number was no coincidence. It was a magical thermostat for life. This temperature was in the ideal range for water to remain liquid. But it was also cool enough to prevent complex organic molecules from breaking down. On Earth, some of the most extreme life forms, large thermophils, thrive in this exact temperature range. This meant K218b might not just be habitable, but actively optimized for life. But how was this constant temperature maintained? The answer was in the planet's thick hydrogen atmosphere. This atmosphere acted like an insulating blanket, distributing heat evenly across the entire planet. Therefore, even its dark side, which never sees its star, maintained this comfortable temperature of 49 degrees. This was something impossible on Earth. Our planet has huge temperature differences between the poles and the equator, between night and day. But K2-18 was a stable, warm paradise across its entire surface. This meant life could thrive continuously, without the stress of seasonal changes, the danger of freezing, or the threat of overheating. This provided an environment where evolution could focus not on survival, but on complexity. But the most mind-boggling thing Webb found was perhaps the atmosphere itself. This was not a simple mixture of hydrogen and helium. It was a complex cocktail of methane, carbon dioxide, and water vapor. And within this cocktail, something incredible was happening. Diamond rains. Yes, you heard that right. Specific pressure and temperature conditions in the planet's atmosphere were compressing carbon atoms to form microscopic diamond crystals. These diamonds were raining down from the sky to the surface. This was a scene that could only be possible in science fiction. But hey, Webb's spectral data confirmed that this process was real. This showed that the planet's carbon cycle was completely different and much more dynamic than ours. This wasn't just an exotic weather phenomenon. It was proof of how active the planet's chemistry was. These diamond rains were constantly transporting carbon from the atmosphere to the surface, incorporating it into geological processes. This was part of a giant, planet-scale system where the essential elements for life were constantly being recycled. This discovery was the most striking example of how bizarre and how wonderful a planet can be. The presence of dimethyl sulfide, the absence of ammonia, the perfect temperature of 49 degrees, and diamond rains. These findings, each revolutionary on its own, when put together, revealed one overwhelming truth. A K2-18b is not just a living world. It is home to a biosphere that is far more advanced, far more stable, and potentially far older than our own. But all these findings allow us to go one step further. They allow us to ask not just, is there life, but what kind of life is there? Because these chemical signatures give us incredible clues about the nature of the life that might exist there. And these clues lead us to an even deeper, even more dizzying universe of possibilities. Because this world may not be following the rules of life as we know it. It may be writing its own rules. And what those rules are is perhaps the greatest mystery of all. Because beneath that atmosphere, in the depths of that hydrogen ocean, because beneath that atmosphere, in the depths of that hydrogen ocean, the limits of biology as we know it come to an end. And, therefore, Webb's subsequent findings were not just shocking, but also dizzying. Because these findings proved that K2-18b was not just a living world. It was potentially a world more habitable than Earth. This idea was once considered heresy. But now, it was supported by data, and it all begins with the planet's enormous mass. This is a record. At 8.6 Earth masses, K2-18b is one of the largest rocky planets whose atmosphere has ever been analyzed. This massive size creates a surface gravity nearly 3 times that of Earth. This seems like a disadvantage at first. But, in fact, It is the planet's greatest insurance policy. This crushing gravity holds the planet's atmosphere like an iron fist. And it protects it for billions, years, even trillions of years. Mars lost its atmosphere billions of years ago. Because it wasn't big enough. Earth is also slowly losing its atmosphere. But K2-18 BA will not. This means an almost infinite amount of time for life to evolve. This should not have been possible. Because standard planet formation theories predicted that a planet this large should have turned into a gas giant like Jupiter. But K2-18b managed to stay in that sweet spot. Big enough, but not too big. This discovery gave rise to a new concept called super-habitability. According to this concept, the most ideal environments for life in the universe may not be planets like Earth, but super-Earths that are larger, older, and more stable than Earth. This idea fundamentally shook the rare Earth hypothesis. We were no longer questioning if we were alone, but whether we had the best living conditions in the universe. And the answer was, most likely, no. But this stability didn't just come from its mass, it came from its star, K2-18, a red dwarf, the most common type of star in our galaxy. And this might be one of the greatest ironies in human history. Because, for years, we thought that planets around red dwarfs were inhospitable to life. But Webb's findings proved the exact opposite. K2-18 can live for up to 10 trillion years. That's 1,000 times the total lifespan of the Sun. That's 700 times longer than the current age of the universe. This is an incredible timescale. This means that life on K2-18b could be trillions of years older than life on Earth. This was impossible. Because such a long period offers possibilities for the levels of complexity evolution can reach that we cannot even imagine. Red dwarfs are known for violent flares in their early stages. But K2-18 had long since passed its stormy youth and had become a calm, stable star. This offered its planet an uninterrupted and reliable source of energy. This discovery completely changed the focus of SETI, the search for extraterrestrial intelligence. We were no longer looking only at sun-like stars. We were now looking at the oldest and most stable residents of the galaxy, the red dwarfs. Because the most complex and intelligent life might have developed in the places that have existed the longest. And Webb continued to search. Everywhere it looked, it found new evidence confirming the universe's tendency for life. This was not about just one planet. This was about the galaxy itself. In Webb's first year of observation, astronomers identified more than 50 potential habitable world candidates in an area just 200 light-years around Earth. This was a statistical revolution. This meant our galaxy could be filled with billions of living worlds, each conducting its own biological experiment. In the Milky Way galaxy, there are about 400 billion stars. If our small neighborhood is this rich, the entire galaxy could be home to more living worlds than there are people on Earth. This should not have been possible. Because the Fermi paradox asked us, if the universe is teeming with life, where is everybody? Webb's answer was simple. They are everywhere. We just weren't looking in the right place. This fundamentally changed our perspective on the universe. We are no longer a rare oasis in an empty space. We are just one part of a giant cosmic forest teeming with life. This was much more than a scientific finding. This was a philosophical enlightenment. Understanding that we are not alone required us to redefine who we are and what role we play on this cosmic stage. Mass, stability, and abundance, but each of these were factors that could make K218, B, and billions of planets like it a better place for life than Earth. What Webb showed was that the universe loves life. It supports it, and it brings it forth in far more diverse and abundant ways than we could have imagined. These discoveries have brought us to a crossroads. All the dizzying data we have collected, all the shocking findings, all the broken records, but now is the time to stop and think. Time to breathe. Because the deepest meaning of these discoveries lies not in the numbers or the spectral lines, but within ourselves. What does all this information, this incredible cosmic perspective, mean for us? What does it say about our place on this small, blue planet? Because knowing that a world is breathing on one end of the universe, 120 light-years away, changes everything. And the nature of that change is perhaps Webb's greatest discovery. Because this is not just the story of a planet. This is our story. And the most important part of that story is beginning now. Because we are no longer. Because we now know that we are not alone in the universe. And now it is time to stop and think. After that dizzying pace, it's time to take a breath and ask ourselves the most fundamental question. All these discoveries, the breathing atmosphere of K218, B, star that will live for trillions of years, the potential for billions of living worlds in our galaxy. What does all this mean for us? For us on this small, pale blue dot. Because this knowledge doesn't just change astronomy books. This knowledge changes us. It makes us rethink who we are, why we are here, and what our place is on this unbelievably vast cosmic stage. And this thought confronts us with the most fundamental human paradoxes. The first paradox is about distance and closeness. On one hand, there is a breathing world in the Leo constellation, 120 light-years away. K2-18b, an unimaginably distant place where even light takes more than a century to reach us. It would take our fastest spacecraft more than 2 million years to get there. That is longer than the entire history of humanity. This is the tragic reality of untouchability, of physical inaccessibility. We will never go to that world. We will never stand under those diamond rains. We will never walk on the shores of that hydrogen ocean. This is the truth that there is an unbridgeable gap between us. On one side, there is us. On the other side, there is them. And between us lies a cold, dark, and merciless void. This is, on one hand, a sad sense of loneliness. But, on the other hand, the very same telescope closes that 120 light-year gap in an instant. The golden mirrors of James Webb capture that faint photon trace left by a single molecule in that planet's atmosphere. And that photon, at the end of its 120-year journey, becomes our eye. In that moment, that 120 light-year distance becomes meaningless. Because we can read that planet's chemistry. We know it is breathing. We can analyze it like a chemistry experiment in our own home. This is the triumph of our mind, of science, and of curiosity. Even though we cannot physically reach it, we are there mentally. You are in the middle of this paradox. You are on this planet, inside a body of about 1.7 meters. But at the same time. With your mind, you can think about the atmosphere of a world 120 light years away. You may be physically limited, but your capacity to understand is as limitless as the universe itself. This is to experience both the tragic smallness and the glorious greatness of being human at the same time. The second paradox is about time and the moment. On one hand, there is a universe that is 13.8 billion years old, and within it, there are stars like K 2-18 that can live for 10 trillion years. This is almost an eternity. On this time scale, a human life of 80 years is shorter than the blink of an eye. We exist on this cosmic calendar for a period more insignificant than a speck of dust. Our entire civilization, all our history, all our wars and peaces are like a drop lost in this vast ocean of time. This is the tragic shortness of existence. We are but momentary witnesses to this universal play. And there were trillions of years before us. And there will be trillions of years after us. This can create a sense of nothingness and insignificance. But on the other hand, it is this very brief moment that makes everything meaningful. Because we are in that special moment in this 13.8 billion year history when the universe became aware of its own existence. We are beings made of stardust, Awaki, who now look at those stars and solve their secrets. The consciousness that built the James Webb Space Telescope analyzed that data and could say, there is life there, is the product of this very short human life. This means that an 80-year life can be more valuable than trillions of years of silence. Because what matters is not how long we live, but what we understand in that short time. You are part of this paradox. You have limited time, but within that limited time, you can contemplate the infinity of the universe. You can imagine the trillion-year future of K 218. This makes your existence both tragic and miraculous. You exist for just a moment. But that moment is the moment the universe is trying to understand itself. The third paradox is about knowledge and mystery. On one hand, we have the most powerful information-gathering tool in human history. James Webb. It gives us data we have never had before. We can measure the chemicals in a planet's atmosphere with a precision of 1 part per billion. We can see how galaxies are born. We can shed light on the darkest corners of the universe. We know more now than ever before. We know there is dimethyl sulfide in the atmosphere of K 218 b. We know that planet is 49 degrees. We know we are not alone anymore. This is the triumph of enlightenment, of knowledge, and of certainty. But on the other hand, every new answer brings with it 10 new questions. Every illuminated corner reveals a greater darkness behind it. We found dimethyl sulfide, but what does the life that produces it look like? We saw the diamond rains. But how does that planet's geology work? We understood the stability of red dwarfs. But does intelligent life that develops there resemble us? Every new piece of information actually slaps us in the face with how little we know. The mystery of the universe does not diminish as knowledge increases. On the contrary, it deepens. This is the tragic but also beautiful nature of science. It's like the horizon. No matter how far you advance towards it, it always remains that far from you. But Sikji, what matters is not reaching the horizon, but being on that path. You are in this paradox. You learn new things every day. But everything you learn reminds you of how much you do not know. You are both the knower and the non-knower. both enlightened and still searching for your way in the dark. And this is the most fundamental truth of being human: to wonder, to search, and to continue searching, knowing that you will never fully find distance and closeness, time and the moment, knowledge and mystery. These paradoxes are the fundamental pillars of the new picture of the universe that Webb has presented to us. They are truths that both diminish and exalt us. But there is much more to discover on this journey of thought. Because these discoveries are reshaping not only our relationship with the universe, but also our relationship with each other. This cosmic perspective confronts us with our most basic human responsibilities. Because looking at that pale blue dot from 120 light-years away makes everything look different. And this new perspective, perhaps, holds our greatest hope. Because when we listen to that silence in space, perhaps what we hear most is our own voice. Because when we listen to that silence in space, perhaps what we hear most is our own voice. And therefore, the fourth paradox is built on loneliness and togetherness. On one hand, there is the mind-boggling vastness and emptiness of the universe. Our nearest neighbor star, Proxima Centauri, is 4.2 light-years away. K2-18 Peak is 120 light-years away. The Andromeda Galaxy is 2.5 million light-years away. These numbers represent the immense, large quartz, cold void between stars and galaxies. This is the foundation of what we call cosmic loneliness. We are like an isolated island, floating in this vast emptiness. This is the deep, jacked, existential loneliness that humanity has felt for thousands of years. This is why we look at the sky and ask, is anyone out there? Because this silence can be overwhelming. This emptiness can be frightening. This is a tragic fact that traps us in our own little world, our own little problems. But on the other hand, there is another truth that Webb shows us. Life is not a rare exception, but a universal possibility. If there are billions of living worlds in our galaxy, then we are no longer alone. We are part of a cosmic family, larger than we could ever have imagined. We may not have met them yet. We may not have heard their voices. But we know they exist. This does not eliminate our loneliness. It transforms it. We are no longer a lone voice shouting in an empty universe. We are just one of countless voices in a giant choir. And this choir is singing the song of life. But you are in this paradox. You may feel lonely in your daily life. But now you know that you are part of a giant web of life, spread throughout the universe, breathing, growing, and evolving. You share a fundamental connection with a being on a world 120 light-years away, perhaps breathing with a completely different chemistry. You are both children of the universe, and this, even in the deepest moment of loneliness, is a powerful sense of togetherness to remember. The fifth and perhaps most important paradox is about power and responsibility. On one hand, there is the incredible technological power we as humanity have achieved. We are a species that can send a gold-plated telescope the size of a tennis court 1.6 million kilometers away. We are a species that can count the molecules in the atmosphere of a planet 120 light-years away. We are a species that can look at the beginning of the universe, understand how stars are born and die. This is immense power. This is a triumph of our intelligence and our curiosity. This power gives us a sense of control over the universe. It gives us the belief that we can shape our future. determine our destiny. This is the sweet intoxication that comes with enlightenment and progress. But, on the other hand, there is another truth that these discoveries remind us of: our fragility, our responsibility. Webb doesn't just show us how wonderful other worlds can be. It also reminds us how precious and how delicate our own world is. Our atmosphere, our oceans, our biosphere, these are a priceless treasure, the result of billions of years of evolution. And we are the only species with the power to protect this treasure. But we also have the power to destroy it. Discovering K218b, PHB is in a way holding a mirror up to our own home. When we see that planet's stability and longevity, we understand how fragile our own planet is. This is a tragic awareness. The fact that our power can also be our greatest weakness. You are at the very center of this paradox. You are one of billions of people on this planet. But your choices, your actions, affect the future of this planet. You are both part of the problem and the solution. This cosmic perspective places a responsibility on us, not just to our own species, not just to our own planet, but to all life in the universe. Because if life is so common and so diverse, then protecting it becomes a universal duty. After learning all these discoveries, how do you feel? On one hand, an overwhelming sense of smallness and insignificance in the face of the universe's vastness? Do you think your own existence is nothing more than a momentary flicker against timescales of billions of years and distances measured in light years? Or is it the opposite? On the other hand, do you feel a deep admiration and pride for being part of this giant cosmic structure? For being a conscious entity that can understand it, question it, and even solve its secrets? Both are true, both are valid. Because to be human is to oscillate between these two feelings. We are both stardust and the stargazers. We are both infinitely small and large enough to comprehend infinity. This is perhaps the greatest lesson Webb has taught us. The universe is a place full of contrasts, and we are the most perfect example of those contrasts. Contemplate the infinity of the universe. You can imagine the trillion-year future of K218. This makes your existence both tragic and miraculous. You exist for just a moment. But that moment is the moment the universe is trying to understand itself. The third paradox is about knowledge and mystery. On one hand, we have the most powerful information gathering tool in human history. James Webb. It gives us data we have never had before. We can measure the chemicals in a planet's atmosphere with a precision of 1 part per billion. We can see how galaxies are born. We can shed light on the darkest corners of the universe. We know more now than ever before. We know there is dimethyl sulfide in the atmosphere of K218b. We know that planet is 49 degrees. We know we are not alone anymore. This is the triumph of enlightenment, of knowledge, and of certainty. But on the other hand, every new answer brings with it 10 new questions. Every illuminated corner reveals a greater darkness behind it. We found dimethyl sulfide, but what does the life that produces it look like? We saw the diamond rains. But how does that planet's geology work? We understood the stability of red dwarfs. But does intelligent life that develops there resemble us? Every new piece of information actually slaps us in the face with how little we know. The mystery of the universe does not diminish as knowledge increases. On the contrary, it deepens. This is the tragic but also beautiful nature of science. It's like the horizon. No matter how far you advance towards it, it always remains that far from you. But Sikchi, what matters is not reaching the horizon, but being on that path. You are in this paradox. You learn new things every day. But everything you learn reminds you of how much you do not know. You are both the knower and the non-knower, both enlightened and still searching for your way in the dark. And this is the most fundamental truth of being human: to wonder, to search, and to continue searching, knowing that you will never fully find distance and closeness, time and the moment, knowledge and mystery. These paradoxes are the fundamental pillars of the new picture of the universe that Webb has presented to us. They are truths that both diminish and exalt us. But there is much more to discover on this journey of thought. Because these discoveries are reshaping not only our relationship with the universe, but also our relationship with each other. This cosmic perspective confronts us with our most basic human responsibilities. Because looking at that pale blue dot from 120 light years away makes everything look different. And this new perspective, perhaps, holds our greatest hope. Because when we listen to that silence in space, perhaps what we hear most is our own voice. Because when we listen to that silence in space, perhaps what we hear most is our own voice. And therefore, the fourth paradox is built on loneliness and togetherness. On one hand, there is the mind-boggling vastness and emptiness of the universe. Our nearest neighbor star, Proxima Centauri, is 4.2 light-years away. K2-18 P is 120 light-years away. The Andromeda Galaxy is 2.5 million light-years away. These numbers represent the immense, large quartz, cold void between stars and galaxies. This is the foundation of what we call cosmic loneliness. We are like an isolated island, floating in this vast emptiness. This is the deep, jacked, existential loneliness that humanity has felt for thousands of years. This is why we look at the sky and ask, is anyone out there? Because this silence can be overwhelming. This emptiness can be frightening. This is a tragic fact that traps us in our own little world, our own little problems. But on the other hand, there is another truth that Webb shows us. Life is not a rare exception, but a universal possibility. If there are billions of living worlds in our galaxy, then we are no longer alone. We are part of a cosmic family, larger than we could ever have imagined. We may not have met them yet. We may not have heard their voices. But we know they exist. This does not eliminate our loneliness. It transforms it. We are no longer a lone voice shouting in an empty universe. We are just one of countless voices in a giant choir. And this choir is singing the song of life. But you are in this paradox. You may feel lonely in your daily life. But now you know that you are part of a giant web of life, spread throughout the universe, breathing, growing, and evolving. You share a fundamental connection with a being on a world 120 light years away, perhaps breathing with a completely different chemistry. You are both children of the universe, and this, even in the deepest moment of loneliness, is a powerful sense of togetherness to remember. The fifth and perhaps most important paradox is about power and responsibility. On one hand, there is the incredible technological power we as humanity have achieved. We are a species that can send a gold-plated telescope the size of a tennis court 1.6 million kilometers away. We are a species that can count the molecules in the atmosphere of a planet 120 light-years away. We are a species that can look at the beginning of the universe, understand how stars are born and die. This is immense power. This is a triumph of our intelligence and our curiosity. This power gives us a sense of control over the universe. It gives us the belief that we can shape our future, determine our destiny. This is the sweet intoxication that comes with enlightenment and progress. But, on the other hand, there is another truth that these discoveries remind us of: our fragility, our responsibility. Webb doesn't just show us how wonderful other worlds can be. It also reminds us how precious and how delicate our own world is. Our atmosphere, our oceans, our biosphere. These are a priceless treasure, the result of billions of years of evolution. And we are the only species with the power to protect this treasure. But we also have the power to destroy it. Discovering K218b, PHB is in a way holding a mirror up to our own home. When we see that planet's stability and longevity, we understand how fragile our own planet is. This is a tragic awareness. The fact that our power can also be our greatest weakness. You are at the very center of this paradox. You are one of billions of people on this planet. But your choices, your actions, affect the future of this planet. You are both part of the problem and the solution. This cosmic perspective places a responsibility on us, not just to our own species, not just to our own planet, but to all life in the universe. Because if life is so common and so diverse, then protecting it becomes a universal duty. After learning all these discoveries, how do you feel? On one hand, an overwhelming sense of smallness and insignificance in the face of the universe's vastness? Do you think your own existence is nothing more than a momentary flicker against timescales of billions of years and distances measured in light years? Or is it the opposite? On the other hand, do you feel a deep admiration and pride for being part of this giant cosmic structure? For being a conscious entity that can understand it, question it, and even solve its secrets? Both are true, both are valid. Because to be human is to oscillate between these two feelings. We are both stardust and the stargazers. We are both infinitely small and large enough to comprehend infinity. This is perhaps the greatest lesson Webb has taught us. The universe is a place full of contrasts, and we are the most perfect example of those contrasts. Now we know that the universe is much more alive than we thought. We know that the conditions required for life are not limited to our planet. We know that our galaxy is filled with billions of potential cradles of life, each telling its own story. And most importantly, we know that we are not alone. As we approach the end of this long journey, all this information comes together in our minds: distance and closeness, time and the moment, knowledge and mystery, loneliness and togetherness, power and responsibility. All these paradoxes define our new place in the universe. This journey was not just about numbers and discoveries. This journey was about perspective. It was about looking at ourselves, Okazaki, the universe, Watzia, and the relationship between them with new eyes. And now, with this new perspective, we are ready to ask one final question. What will all this change for us when we wake up tomorrow? Because the true value of a discovery is not what it is, but what it does to us. And the discovery of K218b will change us forever. Because every generation before us looked at the sky and wondered. But we are the first generation to look at the sky and know And this knowledge, on this journey, we discovered that we are not alone in the universe, that other worlds are also breathing. But I haven't told you something. What if on one of those worlds, there is another you watching this video right now? Infinite universes, infinite possibilities, and a new reality created by every decision. On our next journey, we will push the limits of the multiverse theory. Are you ready?